Okay, so we come now to the final presentation of the final team. And the presentations you heard the last 2 days were basically, I mean, for those of you who know these workshops, you know teams can have sort of very broad themes or very sort of well-defined, sort of more narrow themes. I think the teams that were presenting yesterday were sort of well circumscribed. Ours is kind of more broad in its coverage, which I think is actually an interesting thing to be. But in any case, basically what we're going to be talking about is broadly comes under the term of multilingual spoken or term detection or spoken term detection. And the basic idea is the following. I mean, people have lots and lots of ways of saying the same thing. Okay, they can have lots of different ways of expressing the same idea. They can appear in writing in different forms. So if you look at how a given name may be written in different languages, it's going to be written, spelled in different ways. It may show up in different languages in speech, in different pronunciations. So that's sort of the general unifying theme of this whole team. Okay, the basic things we're looking at is new source.
There is a question.
Yes. Already?
Oh, yeah. So are you
It's too early for questions, George.
Are you going to tell us what a term is?
No. Thank you. That's right.
Could anybody else tell us what a term is?
Well, I mean,
People are obviously in need of instruction.
well, I think it'll become clear the kinds of things that we're dealing with here. I mean, so
The person who came up with the term is the person.
right, the term spoken term detection is
To my right.
right.
I have no idea.
Okay. Well, think of it as a name for something. Often a personal name, a place name, an entity name of some kind. That's typically what we're dealing with, but the kind of techniques we're talking about in principle don't depend upon it referring to any particular kind of thing. So a term is a word or a phrase or something like that in a language.
Actually, term is what's called a term.
Right. That's another way to put it. Okay, so we're interested in ways of finding new pronunciations. We'll be talking about that. Also in finding the same form in that occurs in different languages across different writing systems, different scripts. We're also interested in ways of testing these. Obviously, we want to know whether we're doing a reasonable job. We'll be looking at that. And where speech recognition comes into this is obviously one of the applications of pronunciations is in speech recognition, improving speech recognition. But as we'll see, speech recognition itself can also be used to sort of evaluate pronunciations independently of whether you're actually using those pronunciations in a particular speech recognition system for a particular application. So basically, I'm not going to say much more here. I want to spend more time on the actual sub-teams. So basically, what we're going to be hearing about today, starting with the first sub-team, which is going to be talking about how to find pronunciations, in particular finding pronunciations on the web. As we'll see, there are millions of pronunciations out there that could be useful. The second sub-team will be talking about how we can look at finding transcriptions across different scripts. And finally, the third sub-team will be talking about applications of these within the context of spoken term detection or, more generally, automatic speech recognition. So with that, I'm going to hand it over to Michael.
Good morning. I'm going to be kick off this sub-team's effort, which we're calling web-derived pronunciations. These are the people in the team. And so what's the problem? The problem is how do you find pronunciations of words for various applications? Speech recognition, speech synthesis. We're talking about STD here as well. And the previous approaches done in the past have consisted of essentially two categories that I know of at least. One is you either buy or hire people to compile a dictionary by hand. And this takes some training and can be expensive. And you have questions of coverage. Or the second method is you handcraft or you machine learn a set of rules that will generate new pronunciations for words you haven't seen. And the problem with that is you get variable quality. It depends on what you train on, et cetera. and the methods you use. Our new approach is a third way, and that is taking the advantage that now there are people all over the world are writing web pages in which they're telling us what they think the pronunciation of various words are. Either on this can go from dictionary websites to people having the IPA of their name or some other way of putting their name on their home page or something. And we break it broadly into two categories: those which give the International Phonetic Alphabet of some terms. So here's actually an actual example drawn from a web page where somebody says blah, 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 Lorraine Albright, and then they give the IPA symbols for that pronunciation of Albright. And second example is what we're calling ad hoc pronunciations, where people, instead, they give the pronunciation something outside of IPA. Often it's done in this sort of mock English syllable sound. So they're saying bruschetta, favorite food of mine, is pronounced bruschetta. Okay, not bruschetta, some people say, including people in restaurants. We're dividing the problems into three broad categories. The first step is going out and finding these things on the web. Step one was pretty much done inside of Google, almost by necessity, because we had to crawl the web and then go over a very large set of documents looking for these sorts of things. And once we've found those, we have a second step where we look at them more carefully and decide whether they're right or not. And the question there is basically, did we extract what the person intended for us to see as the pronunciation? So here's an example. Basel pronounced Brazil by the lisping Broca. We actually extracted Brazil by the lisping Broca. So we made a misextraction there, and we call that wrong, and we'd like to either reject it or correct it. In fact, this is an example where we might be able to sort of correct it if we'd somehow dropped off the by lisping Broca, but in most cases, actually, it's hopeless. If we misextracted it, the answer often isn't even there. For instance, it could say Basel pronounced dead, in which case there's really no right answer at that point, just that we don't want to use that. It's not a pronunciation. A second kind of problem is we might have extracted it correctly, and here's an example here. I can't pronounce this guy's name. Dijanan, pronounced I'm a mad dog Jihad. This is, we extracted what the person intended us to get as the pronunciation, but here it's a facetious one. Other cases it's just wrong, for instance, or other problems. For instance, had we extracted this correctly, Brazil would still not be a good pronunciation of Basel, so we should try to reject it under the third category. So we'll be talking about these three steps going forward. And so for the first step, essentially, we do it differently if it's the International Phonetic Alphabet type pronunciations or if it is the ad hoc. In the IPA type case, we're helped a lot by the fact that many of the symbols in the IPA are not normal characters, and they reside in a special code block in the Unicode set. So we can go look for terms which contain one or more of these special characters, and all the other characters correspond to things that could be IPA. Like ASCII characters and whatnot, and furthermore, if we're looking for things on English, we can restrict it to things that had to be in the English IPA set. Once we found those as putative candidate pronunciations, we then need to find the matching orthographic string that we think corresponds to that, and that's relatively straightforward. We just need a conditional model that says, given a pronunciation, what's the orthography, and then we can apply that to words nearby the pronunciation we found and attempt to, and we find the best match. And the particular mechanism we use is a finite state transducer, but that's a nice implementation detail that makes it work well, but it's not necessary for understanding this. Okay. And with this, when we run this over our internal corpus, we get something like 3 million English extractions and 370,000 unique ones. Unique.
Internal corpus?
The web.
Oh, I thought you said internal.
Internal to Google. Okay. Okay, so it's pretty much what you can see when you type a query. So restricted to pages which we label as English internally. Okay, it's a lot. Okay, then in the second case, we're looking for these so-called ad hoc pronunciations like bruschetta, right? Here it's a little harder. What we're doing is pretty good at, we get, by our methods, we get a lot, 5 million of them. We just set regular expressions up and we say, okay, let's look for something where somebody says, for instance, left paren pronounced as like and then whatever's there. Other cases, we might say pronounced and something in quotes, or comma pronounced. We have a few handful of regular expressions, and we could extend them, but we pretty quickly found a lot of data that to work with. We didn't need to look for more, but presumably we could find more if we expanded our regular expressions. Okay, this finding the orthography gets a little more complicated now, because now you're matching one orthographic string with another one being a more complex representation, bruschetta, and the other is written, and then bruschetta. So the idea is to use essentially two letter-to-sound models, which you assume there's some latent pronunciation, which you sum over to build a model from essentially from the ad hoc pronunciation to the orthographic term. And then again, the same deal, we look over words nearby and find the maximum one, and that is what we extract. Okay?
When you say 740K unique ortho-pron pairs, is this over and above some base dictionary you're using, or this is just...
That's about the same, frankly, because the number of, the overlap with IPA is small, which Sanji will describe later. Okay.
So the two factors in that probability model, are they marginalizations of the same distribution?
At the moment, yes. One question could we do a better job, and it's a very simple model. It's actually a unigram model, but some preliminary experiments trying to improve that didn't. I mean, essentially, we saw that the mistakes we were making were hopeless. So, sort of doing something fancier in the second stage in validation was a reasonable strategy, and we'll talk about using different models in the second stage.
Thanks.
Okay. But keeping it simple in the first means it runs fast, and we didn't have to repeat it because it takes a long time.
Do you only find the one best thing in the context to validate, or?
That's what we do. We could do more, but again, as I say, it's either right or it's hopeless. So from our own, we took a sample of 1,000, and we looked at the mistakes we made and said, could these be fixed? And there were very few we could fix. It was either we got it right or it was bad.
Yeah, if you want to go to details, the two models are not symmetric, right? You want the pronunciation of the ad hoc form, the 5 given the ad hoc form, to be simple, because people are trying to write a simpler form to pronounce. But the second one, also 2 given 1, is presumably a difficult one. That's why someone's telling you how to pronounce it.
Right.
So these
That's
are
why I asked.
Right.
But
So
in our case-
in this first extraction, saying they were the same because that's how we bootstrap. But later on, they definitely diverge. Okay. And then the last point I want to make is just what kind of models are we using here, and letter-to-sound models, and it applies to the extraction we described, and pretty much everything we're doing. We kept it simple. We used a technique which Bazani and Herman Nye have published on, and the simple idea is you simply align your orthographic string with your phonetic string, and then you build an n-ground model over the pairs. Okay? And then when you predict, you convert it to a finite state transducer, you apply the transduction on the orthographic string to the transduction, and you read off the one or more best of the phonetic strings. The advantage of doing it this way is that now we have transducers, we can compose them, we can do various experiments. It was very, very convenient for our work here. And it's a pretty competitive system, too. Okay?
And we should probably clarify that the second string is the IPA string alphabetized.
Yeah. For the slides, we've often, because at least several of us know ARPABET best, and because it's ASCII, we convert a lot of the stuff to the ARPABET for display and internal use. But it's one-to-one mapping with the English IPA. Okay. Now I will turn it over to Morgan, who will talk about extraction validation. The alignment starts with we start with a small amount of pronlex to build the alignment, but it's only a unigram model, so it's a very weak sort of thing. We could have started, right. We could have used, for instance, a scrape of Wikipedia if we had no data in the given language. I should add, by the way, we've actually done some extractions as well in French and German, but we haven't used them in this workshop, but we get a fair amount of data in other languages.
Okay, so I'm going to talk about validating the extractions after we've gotten them from the web. So there are the two parts, the IPA and the ad hoc, and I'll start by talking about how we validate the IPA extractions. So our goal is that after the extraction has taken place, we want to filter out the incorrect extractions and keep only the correct ones. So we started by hand annotating 667 of the examples from the extraction. And then we trained an SVM classifier using 16 features. And the features we decided to use were the language model score, as Michael described in the previous part, the probability of the orthography given the pronunciation. And so then the distance between the orthography and the pronunciation, so how far apart they were actually in the text. The length of each of the orthography and the pronunciation, presence of space in the orthography, and some alignment-based features. So what we did was we used the letter-to-sound model to predict the pronunciation from the orthography, and then align that with what we extracted from the web. And we separated out the consonant and vowels and looked at them separately, and then used features based on how those two things were aligned. So the results from this were 85.8% accuracy, 99.6% recall, and 85.0% precision, and 92% area under the curve.
Question? I missed the language model score. What's the language model score?
It's probability of the orthography given the pronunciation based on, yeah.
That's fine, thanks.
Right. So, and as Michael talked about, we want to choose precision over recall. So if you look at the curve, we can improve our precision quite a bit by sacrificing some of the recall, and we can get up to 96.2% precision and still have 88.2% recall. So that's pretty good. So then the next part is validating the ad hoc extractions, and the process is very similar. We want to filter out the incorrect extractions. We hand annotated 1,000 examples in this case and trained the SVM with 57 features. Again, we have the language model scores. In addition to just the original orthography given ad hoc, we have some per phone alignment scores out of the language model alignment. And so the cost of each alignment of the phones, and also the number of insertions and deletions from that alignment. Counts, how many times did that orthography and that pronunciation appear in our corpus, and how many times did that domain appear? Also, we looked at how many unique domains did the orthography occur in, and how many unique domains did the ad hoc occur in. So that kind of gives us corroboration over multiple domains. Presence of function words in the orthography and the pronunciation. Oftentimes we'd pick up some extra stuff along with the pronunciation, and function words is kind of a good way to catch that. And also non-alphabetic characters. Distance between the orthography and the pronunciation, again, similar to what we did for IPA. And also the capitalization style of the orthography and the ad hoc pronunciation. And here are results, five-fold cross-validation again. We had 93.7% accuracy, 95.9% recall, and 95.3% precision. And actually, we can increase that precision even more. We can get it up to 98.1% and still have recall of 87.5%. So 98.1 is very good precision.
Excuse me, can you tell us which of these features is which are the most important features?
We get the most out of the language model scores, and all the rest of them are kind of small improvements on that.
Small
Yeah.
Question?
Yeah.
Somehow it would seem, the first one was for the extraction of the phonetic pronunciation. This is for the ad hoc
Right.
pronunciation. Somehow it looks like the ad hoc pronunciation extraction performs better than the phonetic extract, which seems counterintuitive to me at least. Is there
Basically, because we had a more complicated model for that, we hadn't trained additional features yet in the IPA side. So I assume if we had 57 features on that side as well, it would have comparable.
So you're saying don't read too much into it.
Right, yeah.
We had the same intuition you did, so more effort was poured into the ad hoc.
Okay, I repeat it.
Yeah.
Okay.
Not all the steps.
Yeah. So in summary, we found that we're always going to have errors when we're extracting from the web. And as Michael talked about that before, it seems to us to be better to filter out those incorrect examples afterwards. And we found that after the extraction has taken place, we can successfully filter out most of those incorrect examples using the SVM models. Okay, so I will pass it on to Arnab now. Yes?
Are the remaining errors things like the Vazel versus Brazel that might show you?
Yeah, we will be talking about that,
Yeah.
not in this section.
Which version? The one where this would have hopefully correctly identified that list being broke above was not right. It was an extraction error.
Oh, I'm sorry, but I mean, if you chop that part off.
You chop that
Right.
out, that's a different problem. We can talk about next.
All right. So Morgan told you about we got the pronunciations, then we sort of validated them, created a cleaner set, and I'm going to tell you that we tried to look into these pronunciations and see how good a quality they are. And for that, it doesn't go forward. Okay, it does go forward. For that, we took this Pronlex, which is our hand-built dictionary, and we considered that our golden reference. And we wanted to see how good the pronunciations that we get from the web are compared to this hand-built dictionary. So we took the intersection of these two dictionaries. We took the common words. For each word, there are two sets of pronunciations. And for each of these sets of pronunciations, we can build a lettered sound model. We did a 5-fold cross-validation, take 80% of the data, build a letter to sound model, test on the remaining 20%. And so this way you have 2 lettered sound models and 2 reference for the test. So you have 4 numbers. And you did this for 5-fold. And oh, by the way, since Richard insists that we shouldn't mix Latin and Greek, I call it polygram, which probably nobody would understand now. It's n-gram. So the numbers look kind of odd, right? Because if you train on Pronlex and use Pronlex reference, you get the best result. But if you train with the web data, the error rate, like on itself, the self-consistency of web data seems about half as good as Pronlex, or the error rate is double. And also the observation is that each of these models trained, the models trained using Pronlex pronunciations does a bad job of predicting the web pronunciation. Models trained on web pronunciation does a bad job of predicting the Pronlex pronunciation. So we redid this experiment for each of the top 10 websites by frequency of pronunciations. And the graph looks like this. So there are a couple of very interesting observations here. One is that for most of the frequent websites, they're internally as self-consistent as Pronlex, because the red line, yes. So the red line is the red number, which is web data, trained on web data using the reference of the web data. So the red line is, the purple line is you train on Pronlex, you use the Pronlex reference. The red line is you train on the web data, use the web reference. And orange and green are the cross numbers. So there you go. So you see that for quite a few of the top 10 websites, the red and the purple lines are close together, which says that these websites are as consistent as Pronlex in assigning pronunciations to words. However,
Could you just say that what's the measure of correctness here? It's
this is phone error rate.
Strings that are generated using the pronunciations you extract to build a letter to phone model. And then you go back, you then generate the phone strings and then you compare them. Okay.
Exactly. And however, as you can see from the cross numbers, that even if it's as consistent as Pronlex, it does a very bad job of predicting the Pronlex pronunciation, and so does Pronlex in predicting the web pronunciation. And the question is, what's happening here? So I just looked up, a few of the words which appear on a bunch of websites and has a bunch of pronunciations, and I picked what most people will consider a very neutral word, well, though some may not. So you see that the bottom ones are the Pronlex pronunciations, and the different websites have different variations, and most of them are kind of reasonable variations of the pronunciation. I would like to draw attention to, there's one, the Pearson.ch. Oh, I have a stick. Okay, yes. So this site, for example, that's like an extraction error, which even after the validation and everything, it still went through. So then the question is, sorry, yes. So the point is that if we have this type of variations, it's not inconceivable that if we train our letter to sound models on these, I mean, we probably wouldn't be doing such a good job of predicting those, and vice versa. And so I'm putting the errors in code because, I mean, we don't know which one is error in this case. Like, we are taking Pronlex as our golden reference, but we know that the other variations are reasonable too. So the point is that in our letter to sound models, we are essentially taking a string of an orthographic string and transducing it to generate this phoneme strings. And we can do the, yeah, sorry.
I was just noticing here, sorry. Was one of your features when you're filtering up bad pronunciation whether or not the entry came from a dictionary?
How do you know whether it came from a dictionary?
Well, I'm just looking at your list. It looks like all the entries that are right are dictionaries, and the one that's wrong is not from a dictionary.
Oh, that's not always true.
It just turns out that the most frequent source of IPA on the web as by domain are the dictionary sites. There's a long tail where,
It seems to be almost certainly true for English. Is that true in general?
I don't think we know.
Also, things like wordreference.com, do we know it's a dictionary? I mean, you might, but how will a computer know it's a dictionary?
Wikipedia that organization. Noah's Ark Cardinals.
Okay. So the point was that we thought, we are already transducing one string of symbols to another string of symbols, so we can do the same with the phone sets. So the idea being that if we take the phone sets, the common pronunciations, we take the Pronlex words, and we see which of them occur in a particular website, say dictionary.reference.com, and we see how their pronunciations are on these two dictionaries. And the hope is that if there is a systematic, either a systematic convention on dictionary.com which renders these phones different, we'll learn that mapping. And so we did that, and lo and behold, everything got fixed. And this is like a random example I picked up, and it looked so good that I was then trying to find something worse. But anyway, so the point is we can fix these errors, or these variations, and sort of normalize the dictionaries from the web to look more like Pronlex. And if we do that, we start seeing improvement. So the orange line is as before, which is without any normalization, and the green line is normalizing with a unigram model. So you see that unigram model is just a permutation of your phone set, and that for a number of websites is already giving you a big improvement. And if you go, yes?
Explain a little bit more about the phone correction model and how it's fair and it is not, it doesn't know that we're graduating from Pronlex, correct?
Yes. Sorry, say that again?
Just what information is in the correction
Is this
model?
just regularization of conventions?
Yes. So the way this model is trained is I get a bunch of data, I train this correcting model, then applying it to, this hasn't seen the data that it's going to be tested on, for example, the correcting model.
This learns the regularization.
And it also doesn't know that the word is graduate and the pronunciation, like the orthography is graduate.
It's a pure
phoneme to phoneme
correction model.
So
But
basically you learn.
what's the training set?
The training set, okay, for okay.
You eliminated the hypercorrect graduate.
For these experiments, the training set is I take the intersection, I do an full validation, right? I take the 80%, train that on that, the correcting model, use that to correct the 80%, train a letter to sound model, and test that on the remaining 20%.
Again, you're building the correcting model off of Pronlex. Pronlex you take as, and then you can then learn a set of rewriting rules or mappings, however you're doing it, by just taking the pronunciations you have in common and mapping them to make them look by parlance, and then you wind up you train a new set of...
Retraining the letter-to-phoneme models.
You don't try to learn farm speech along the way.
No, but a key point is, A question is how much pronouns do we need to do that to come to that. The second point is that this correcting model did not see the test examples.
It didn't see the test.
Which is important, otherwise you could just memorize.
Right, of course, yeah.
I mean, the original idea here was we saw some sites where they actually the phone sets have been permuted in some way. They flipped the letters, when they used the conventions they used. It wasn't strictly IPA, they had all the information. So we're trying to decode their code, if you will.
And somebody had double A as A.
Yes. Now, for something like graduate and graduate, which might actually reflect legitimate pronunciation differences as apart from convention, what happens in such a...
See, as you saw, it actually did the right thing.
So in that
Kept
case,
both.
if it was in the test data, that example, that token would permit 2 right answers. And if our spelling to sound system came up with either one, it would get full mark.
Which is what happened here.
If it's in Pronlex to begin with. But I'm just saying in general for arbitrary new...
For new words.
Right.
Interesting problem, and I'll
Well, you're seeing exactly what happened here. Assuming graduate was not in the, it wasn't, right? This was not in your training set. There were both versions were found on the web, and they were both corrected to the two Pronlex entries.
Because there were 2 Pronlex entries.
No, because the Pronlex entry was not seen by this corrector.
No. Michael's asking, I think, a different question. Suppose there's a new word, right? Some word that's not in Pronlex at all. And we come up with one pronunciation for it, but it admits another correct pronunciation.
You're only coming up with one pronunciation. You're not...
No, you can see right there are 2. Dictionary.reference.com has one, and freedictionary.com has the other. Actually, it has both.
Because you have...
If you came across flingulate, it would do the same thing. It would allow flingulate.
Because you learn a different set of rules for each source?
Yes.
No, Free Dictionary corrected both correctly. It just figures out that in that context,
well, we first of all learn a different set of rules for each source, and depending on what was the original phoneme string in the source, it may get decoded differently. All right.
But I think you did put your finger on an important point. When it comes to pronunciation, there is no single correct answer for any given word, and we just have to deal with it.
And I mean, one concern, sorry?
Yeah, just a scoring question along those lines. So somebody, maybe Sandeep, said that the system gets credit on precision for finding either pronunciation. In order to get full credit on recall, does it need to find both pronunciation?
No.
No, the measure is phone error rate by oracle. So if you lose one and both are in the golden set, then you get full credit.
Another question. Do you ever find that the rewrite rules you learn increase the number of errors in some examples? Actually rewrite the new thing wrong altogether?
This doesn't happen because our, the reference is Pronlex, so it's always getting closer to Pronlex. And
No.
But on test data,
on average, it doesn't get worse.
But some examples, it will. It's not.
It's a statistical system. You know what happens.
So will this process produce simulate as a possible pronunciation of SIMULATE? Let's say, will this process do that?
It would, yes.
Okay.
If a website had it as the long oo, and in other places it was consistently using the E for oo, then the correction rules learned would be to say when you see an oo.
Potentially. It's a 5-gram model, so you'd have to pick a longer one. But maybe regraduate certainly would be fixed that way, yes. Or undergraduate.
All right. Are we moving on?
Yes.
All right. Okay. So yeah, the unigram model already, just a phone permutation for a number of websites is already giving you quite a bit of improvement. You go to bigram, you see more improvement, trigram, and by the time you go up to 5 gram, you're doing just as good as Pronlex.
So in fact, this is the answer to Jack's question. The first green line would do that, and the last green line won't, because it's looking at more context.
Yes. So then the question we asked is, how much amount of Pronlex data is needed? Do we need the whole, the big dictionary to do this correcting? And so we just repeated this experiment with different subsets of Pronlex, and different subsets in the sense you take the 20% most frequent, then 40%, 60, 80, and 100%. So the observation here is that using just about 20% of the Pronlex, we're getting most of the way, and 60% is a bit of improvement, and 100% again we are close to Pronlex. So then another set of experiments that we did was we said that when you build a dictionary, you're going to get the pronunciations for the most common words, and how does this methods do on what would be the rare words? So we got the broadcast news frequency of these words in Pronlex and took anything with frequency 2 or more in our training set and left out anything with lower frequency, and did the same experiment essentially. We using the more common words, but then again subset it into 20, 40 by frequency. We did this normalizing transducer, then built a letter to sound model using just the Pronlex data, the 20% or 40% and so on, and used the normalized web data and put that together with Pronlex and trained another letter to sound model. And these are the three things. So then we take the rare words, we can either look them up on the web using whatever the normalized pronunciation that we obtain, or we can generate the pronunciation based on these two letter to sound models. Okay, so the red line is letter to sound models using Pronlex, the green is looking up on the normalized pronunciation on the web, and the blue is the letter sound model trained using normalized web data and Pronlex. So the observation here is that, well, first of all, these are in some sense hard words, and if you find the pronunciation on the web, just use it. I mean, most letter to sound models will not do as good a job in predicting the pronunciation of the rare words. And the other observation is that even when you use just 20% of the Pronlex data and you look it up on the web, you're doing as good as using the whole Pronlex dictionary to build your letter to sound models. And so the final conclusion is that we can find good pronunciations on the web, and well, there's a lot of details in how you judge which is good and how you use them, but can be done. So I hand it over to Martin.
Okay. Okay, I'm Martin Janche from Google. I'll be talking analogous to what Arnab just described on IPA. I'll be talking about the validation of ad hoc pronunciations. And this is after the extraction validation stage that Morgan talked about earlier. And
ad hoc is the alphabet, is that true?
Yes.
Yes.
That's what's ad hoc about it. Otherwise, it's extracted the same way.
It is extracted by similar convention. We call it ad hoc because there's no single convention how to give a particular pronunciation.
But probably New York Times has one, right?
The New York Times is fairly consistent, but it doesn't follow the same sets of conventions. So, for example, there's an example in the New York Times where somebody's called Mr. Heineken, pronounced like the beer. But where it does, so we have the example, we have an orthographic form of a word that you may not have seen. It's spelled PWN. It's a deliberate misspelling of the word own. And, but I tell you, if you see the ad hoc transcription in green here, this tells you it's pronounced as if it were spelled P-O-N-E, which is pronounced pone, and which is one common pronunciation of this word. And this is online slang. And one of the tasks that we want to solve here is at some point we need to actually predict IPA or ARPA-BET. We actually need to predict what the pronunciation is given the orthography and this ad hoc transcription. The other thing is we need to...
What's the word here? Is it the pone I'm a pawn in your hands or something like that?
No, the word refers to being beaten in an online game. Yes.
Is it a verb or adjective or a noun?
It's a verb. To pwn somebody. You've been pwned. But so I choose this example because it also illustrates the ad hoc pronunciations are quite, in nature, are quite different from what you find in IPA, because there's much less overlap with broadcast news and with prolex. There's a lot of names, there's a lot of unusual words, and there's a bias towards the infrequent and unusual. We also want to, just because we have extracted things correctly doesn't mean we want everything in our lexicon. I'll give you an example in a second. So one of the tasks is we want to filter out the really implausible ones. Second, we need to actually generate the pronunciations. We don't have that directly. This is a much more indirect evidence than if we extracted IPA directly. And third, we want to evaluate how well this is doing. We will do this on the out of vocabulary list from the ASR STD team. And I will talk about these 3 points. So among the implausible ortho-ad hoc pairs I mentioned, there are just people point out weird and unusual things. So look, he pronounces it as nuclear, or there is this person who pronounced the word sausage as sausage. And just because we extracted that correctly doesn't necessarily mean we actually want to retain that pronunciation. And we have tried several techniques to reduce the inventory, and this improves our training in general, so we can threshold by frequency. We have to have seen it a number of times. We can threshold, we can require corroboration. The word must have occurred on different websites, on different domains. If we see it on 3 different websites, we probably trust it more. And once we can score it, we can insist, for example, if I predict the pronunciation from the ad hoc transcription, then the orthography pronunciation pairs must behave similarly to what we would find in prolex. Because we have 3 pieces of information now, a latent pronunciation and 2 different orthographic string, we can constrain them in the triangle, and can constrain all 3 edges and say, this must look reasonable, this must look reasonable, this must look reasonable.
Do you also do anything about rhyming things, you know, some word rhymes with such and so, you filtered that out?
We basically get rid of that in the earlier extraction validation stage, where, remember, Morgan talked about we have these consonant vowel features. If the consonants delete, that's usually a sign of a bad extraction, and on a rhyme you would delete the first couple of consonants, and those are generally gone by here. Now, I mentioned there's these 3 pieces of evidence: latent pronunciation, observed ad hoc, observed orthography. So if we want to predict the pronunciation, we can do simply the models on pairs that Michael talked about earlier. We can try to predict from the orthography, predict the pronunciation, and from the ad hoc, try to predict the pronunciation. And we will do that, and we'll compare how well we can do with either one of these sides of the triangle. And then we have a model on triple where we actually use both of these sources of information and predict from both of them. And on the pairs, predict from orthography is simple. We train a letter-to-phone model on, say, prolex, and we're done, and we're predicting the pronunciation from that. And this is as if we didn't have the ad hoc at all. We can also predict from ad hoc. This is actually, the implementation details are quite tricky, because we first need to actually pair the ad hoc with phones to have training data. And but the way we do this is if the ad hoc is a dictionary word, we just look it up in prolex. And if it's a dictionary word hyphen, something that we can easily predict, then we either predict it or look up by parts in prolex. And then we train an ad hoc to phone model. Now, the models on triples are more interesting. We have 2 models. We have something that I call a noisy dual channel, stereo channel model, where the assumption is the following. We have a latent phone model, which is our source. There's latent phones that are generated somewhere. And there are 2 conditionally independent noisy channels. One turns the phones into an ad hoc transcription, and the other one turns the phones into an orthography. And the orthography is conditionally independent of the ad hoc transcription given the phones. And in the example earlier that you saw, pone, P-O-N-E, gives you the full pronunciation. So the independence assumption is reasonable because we say the ad hoc transcription is a faithful representation of the pronunciation. And so given the ad hoc and the pronunciation, given the pronunciation, and the ad hoc doesn't give you any more information about the orthography than just the pronunciation alone would. And so this is a standard noisy channel model, except we have two channels. We have a generative model over the phones, and we have two conditional models, and we decode. The third model on, the fourth model, the second model on triple is we do a alignment, a three-way alignment of orthography, ad hoc, and phones. And just instead of building a language model, an n-gram model on pairs, we build an n-gram model on triples and do the obvious thing. Okay, about the validation. The original idea was to take all the OOVs from the STD subteam and just evaluate on them. Now, not for all of the OOVs, we don't necessarily have the ad hoc pronunciation. So we have to evaluate on a subset consist of the intersection of the OOV list and those that we have ad hoc pronunciations for. We discovered several problems with the original reference pronunciation. The problem with the original reference pronunciation, it was generated partly by letter-to-sound rules that were not hand-corrected or only hand-corrected or spottily checked. So for example, we have the orthography VE was pronounced as V. So this is an highly implausible English pronunciation. There's many other mistakes. And we decided that what we would end up doing is we would learn how the original letter-to-sound model that generated that reference dictionary worked, and we would end up basically learning those rules and not improving on anything. So basically, we didn't have any independent gold standard. So we created one. And all our results will be reported on that. It is on a smallish side, but it is still around 1,200 phones. It consists of lots of difficult words. Example, this. It consists of unusual pronunciations. So somebody thinks that the ad hoc pronunciation of this word is Roscoe. And we expect, therefore, to see a relatively high phone error rate. But we're interested in we're interested to see what is the improvement from using ad hoc versus using either one of those alone.
When you say somebody thinks, that means you found it on the web.
We found it.
And with it is a text which confirms that that's what they actually think.
Yes.
It's not that you just found two things.
No, somebody said, Rasico, paren, pronounced, quote, Roscoe, end quote, end paren.
So the word pronounced is there.
The word pronounced is always there. Okay. Yes. And these are our results of the best method. Ortho-to-phone is just a model on pairs that gives us from orthography to phones trained on ProNex. So this is doing relatively poorly at 30% phone error rate. Ad hoc to phones is doing much, much better. By using the ad hoc transcription, which is much closer to the intended pronunciation, we get 20% phone error rate. And if we use both orthography and ad hoc with the independence assumption and the noisy channel model, we get incremental improvements. And if we use a language model on triples, we get just under 19% phone error rate. And part of this is the incremental improvements due to the models on triples are presumably due to the fact that we need to do better modeling in the end. We haven't tried any more sophisticated models. We have these very simple models that are n-gram models on triples. We run into sparsity issues there. There are questions of how to do the three-way alignment correctly. We are not really exploiting the full information from the author and the ad hoc correctly not fully by doing this independent noisy channel model. So we will do some better modeling in the future. The other thing that we haven't done for ad hoc is the kind of normalization after we have created the different pronunciations that we did for IPA. And furthermore, what we need is a large reference dictionary just transcribed by a neutral party not generated by letter-to-sound rules that covers both common and unusual pronunciations because, as I said before, there's a bias in the ad hoc data towards the unusual, and often the really unusual pronunciations are not necessarily found in ProNex, and we get penalized for that.
So I want to add one thing, is that in this case, you almost need the dictionary to be on triples, knowing the ad hoc, because
for instance, if the dictionary, if your baseline dictionary says graduate, it's pronounced graduate, and then your ad hoc says graduate, written as grad-u-e-a-t or something, I don't know. You've got to have the right thing lined up with the right thing. And that a human needs to do that if you want to get it just right.
Yes. I'm curious about the ad hoc pronunciations. Typically there are words, right? I assume there is certain coverage of these in the pronlex. What's the coverage of these in pronlex?
Sanjeev will mention this 3 slides from now.
Okay.
The coverage of the words.
No, but he's asking a different question. The ad hoc form.
Because that to me, these are the easy words to pronounce. Presumably they are in pronlex because they are frequent words, presumably. So you don't need letter to sound rules for those, right?
That is right. And if we can look it up, we do look them up.
Right.
But
that's your third model, right? That your language model is an approximation, is the lookup by parts, right?
Yes, but this is actually also consists of. So the details are tricky. So I look at the parts and I score them by a language, by a character model on the orthography, and things that look like English. So there's lots of parts that are arg with. Yes, there's lots of parts that are, lots of pronunciations are arg, lots of A's, lots of R's, lots of G's, lots of H's. And so I actually do a step where I build a character language model and look at what are the things that look like English words. And for those we predict from a letter sound model. So some of the...
I'm curious, aren't like the majority of them simple words? I mean, not your ad hoc pronunciations?
I don't have the numbers, but no.
Okay,
interesting. So what people do is they end up using things like, if they wanted a T sound in the middle, they won't use the word T. They'll just put an uppercase T. And things like that. So it's not quite the same.
But they're not very consistent.
Yep. Okay, sorry. Oh, shucks. Okay, all right.
Just a quick question. Text messaging has its own kind of ad hoc vocabulary. Is there any way you could use that in your experiments?
So we haven't seen any of those in the extracted data.
I think he means looking at that kind of data.
But we should look at it. I don't know where we find it.
Perhaps, it starts to slip into email.
Yeah, right. Instant messaging.
In your language model, do you do any, what kind of backup do you do?
We do cats backup.
Yes or no?
Is it?
We do yes or no?
Yes. But your condition.
Right, so Richard tells us that we are running out of time, so I'll try and conclude quickly for our sub-team. So if you remember, there are 3 sort of stages to what we did. We first extracted lots of things that could be pronunciations from the web, and this was work that was done at Google due to the requirements that you really search the whole web. Then we did a validation step where we tried to throw away a lot of the junk, and then what was left from there, we tried to do a little bit of more of a cleaning up. So the first stage is called extraction validation. So we're just trying to validate the extraction done at Google. And then the second step is pronunciation validation or normalization, where we, for example, if 2 different sites use slightly different IPA conventions, we try to normalize them and so on and so forth. So those are the 3 I'm going to summarize. So first on extraction, as far as the web IPA went, we were actually able to extract quite a bit, even in the limited non-EU domains that we searched, because apparently there are some issues with the EU domains. And we got over almost 3 million tokens, which correspond to about 165,000 unique English words. Yep.
In the earlier slide, I thought the number was 370 and 740. Right?
Yes, so there is a slight difference in what we count. We did an earlier run and a later run, and I think Michael may be reporting the later, bigger run. And how much you search is a bit of a variable. Do you want to clarify?
The difference is between unique word pronunciation pairs versus unique words.
Okay, all right, thank you. That's it. So this is just the words, and some of these admit multiple pronunciations, maybe almost 2 per word.
I can harmonize all the numbers except they mean different things.
Okay.
We didn't harmonize the meaning.
Right. And so Michael, one of the things to note is that most of them are not words already covered in pronlex, even though this is English. So what this says is that people out there on the web feel like they have to tell you how to pronounce something if it's not a frequent word. And pronlex, of course, covers a lot of frequent words. That's why most of the words that people do provide pronunciations for are actually not in pronlex. It's even more true for the ad hoc pronunciations. Again, we got close to 5 million tokens corresponding to almost 400,000 unique words. And most of them, in fact, are not in pronlex. So these are names, and these are the kind of things like from the New York Times, which will tell you how names of people and places are pronounced and so on. So in general, the conclusion is that there's lots of human-supplied data out there on the web, a lot of human-supplied pronunciations, and if we can find a way to get it, that'll be great.
So could hierarchy be pronounced Iraq in your...
Someone probably will tell you that Americans they don't know how to say things, and for example, they pronounce...
You would transfer that pronunciation in...
It would show up, yes. It would show up.
Much worse would show up too. Huh? More brackets probably out there.
Yeah, it would show. Okay. So the extraction we would say is reasonably successful. Next, when it comes to validating the extraction, so again, I'll do this in two parts. I'll tell you what we did with the IPA and then with the ad hoc extractions. On the IPA, we were able to do a fair bit of cleanup. This should remind you of one of Morgan's slides. Basically, we found that if from the 3 million, you pretty much can keep 65%, about 35% turns out to be bad stuff that you throw away. And the part that you keep, you can again use her SVMs to sort of do a little bit of further ranking or selection. And if you throw away a small part that you suspect is not good, the remaining part has very high precision. So that's 96% precision on what we keep. So we keep a fair number of entries and with high precision, right? Next, on the ad hoc, this is the part that Martin talked about later. Here again, we keep a fair amount of data. So 85 or 80, more than 80% of the 5 million are kept. And again, on those, you do a little bit of cleanup. You throw away a small 10, 12% data, and what remains has very high precision. So again, if you wanted a single line conclusion, the conclusion is that high 90s precision is possible in generating pronunciations with a very small loss of good data. So not only can we extract a lot of data from the web, we can then pick from that the good part fairly well, with losing just a little bit of the good parts, and we can throw away most of the bad part. So far so good. The story is very good. Next, when it comes to the web pronunciations, here I think we mostly have a success story. So part one, we discovered that the IPA usage varies a little bit from site to site, but many of these sites are extremely consistent internally in how they represent pronunciations. And therefore, if you do a little bit of site-specific normalization, as we call it, earlier we were calling it correction, then we realized, no, we're not correcting it. We're just making everything conform to the Pronlex conventions. Then you get curves like this. This is one of Arnav's curves. So if you're trying to predict a pronunciation of a word, and you consider Pronlex pronunciation the correct answer, then if you use Pronlex for your training, you'd have got this purple curve. If you use the site data for training, you'd get the orange curve. But if you normalize the site data, you get the green curve. So it's as if this, well, not as if. The site gives you as good training data as Pronlex would have. And so you can get stuff from there. And the other thing that's true for IPA extraction is that if you, these spelling to sound training data, it's very useful as spelling to sound training data. So even if you had only 20% of Pronlex, and if you use that to train your spelling to sound system, you probably wouldn't get very good performance. You'd be in the high 10 to 12% range, but adding the site data, which comes for free, you can bring the phone error rates down to 6%. And this is not a whole lot different from having a big Pronlex dictionary to bootstrap from, which only gives you about 4.5%. So basically you can, if you had a new language in which you had a small dictionary, remember the dictionary is needed to start off this whole process because you need those initial spelling to sound rules and so on.
I want to be careful about this conclusion, because in English there are lots of dictionary sites. This may not be true for other languages, so I would be very careful about
Yes, so let me say that about something.
To me, the ad hoc is the more interesting minded
Agreed.
problem.
Agreed. But there are things in other languages also besides English. Yeah. Okay. All right. So this is as far as the IPA goes, right? Okay. Next on the ad hoc, the ad hoc is actually, you're right, ad hoc actually provides much richer coverage. And it does it for many interesting reasons. So for example, BEGIN, you'll probably just find begin as its pronunciation in Pronlex, and some website will tell you it's begin. And same with NICE, it could be nice or it could be nice. And some website will tell you pronounced NIECE or some other way, right? And so this is the reason why it's very useful, because you get these alternate pronunciations from these ad hoc forms. It's also difficult, by the way, because it raises the problem that I think Michael already pointed to, namely, if this is the case, what is the correct answer for BEGIN? What should your spelling to sound system have produced? Right? So because of this, we actually ran into a lot of problems initially in just evaluating how well we were doing with the...
Actually, I have a comment about the evaluation. The evaluation should be on running speech. Yeah, I'm sorry.
It's coming. Yeah. Okay.
What's that?
So we did sort of get out of this evaluation bottleneck a little bit. We took a bunch of words and we sort of decided that this is correct answer. And I think Michael did this by hand. So we did create these alternate correct pronunciations by hand by looking at the word in context. And when we did that, our initial assumption turned out to be true. Namely, if you use the spelling to sound system on the original word, you get a fairly high phone error rate. But if you use its ad hoc pronunciation as supplied by a human and then synthesize the pronunciation, this number, by the way, is not 22. Martin just, I remember on his slide, he updated it to 18% this morning. So you're down to 18. So actually, again, this is a very successful effort. So we can utilize it. But I would still say we have more to do. Because remember, in the IPA case, we're getting phone error rates of 5, 6%. And we're still up at 18. So I think there is more work to be done. We need to figure out some normalization and so on these sides. Right? So these are essentially the 3 parts. And let me see. So again, so in summary, I think as far as the IPA part goes, we've been able to create a nice large dictionary. And the Google lawyers have decided that pronunciations are fact and not copyrightable. So we are free to distribute this dictionary. So we'll put it up on the CLSP website. It's got 138,000 words, 100,000 of which are not in Pronlex. So we are going to expand the coverage a lot. The question about other languages, Salim, we've already done the extraction in French and German. And we get very large numbers of hits. I asked of hits. Basically, like, remember that 5 million and 3 million numbers, Martin gets maybe comparable numbers, right?
We don't know yet. We can bootstrap easily about 700,000 raw entries for French,
okay.
Half of which look reasonable.
Right, okay. And so we talked yesterday about what it would take to do it for Chinese and Arabic, and we've been thinking about where to go with that, yeah.
So I want to amplify a comment you made, which is the ad hoc words must be easier to pronounce, for even the letter to sounders would do much better. So it'd be interesting to measure this, pick a test set and see, even on Pronlex, it might be...
No, that's what the test set is, 256 of words. It's a small test set because that's all we were able to...
I thought he picked the difficult ones. Maybe I misunderstood your test set.
Also, yes, we pick difficult words, yes.
Yeah, but if you go by frequency of ad hoc, presumably there is a small vocabulary of easy words.
Oh, okay. All right, okay, that's something to think about. And these alternate pronunciations, of course, we are hoping will be useful to people working on speech and on ASR. And by the way, we also thought of there are other applications. If you're doing speech synthesis, you would like them. You could use them for name transcription. If you want to know how a name should be transliterated into another language, it helps to know how it's pronounced. And finally, in the process of generating these reference pronunciations for these 256 words, we realized the ad hoc pronunciations are very useful to lexicography. Again, if you want to sit down and write down how something's pronounced, and if a couple of people who speak that language tell you, oh, this word is pronounced H-A-L-E is pronounced Hale or whatever it is, you know how to write down the dictionary entry. So in summary, I think we've made much progress in extracting pronunciations from the web, and I think we've made good use of them in developing letter-to-sound systems, and we'll see how you'll hear in a while how they do in speech, and of course there are many other applications. So let me stop here and see if there are any questions for our sub-team.
We can take a few questions, but we have to be moving on.
Yes. All right.
Okay, so I'm going to change topics a bit here, although, arguably this is still related to the topic that was just discussed and to the topic that's coming next. We have the smallest sub-team here, so there's only 3 of us going to be presenting, so hopefully we can get a little caught up on time. But you're not going to kill me if we are 5 minutes over the break.
I will not kill you in any.
Okay, fine, good. Okay, so let me start off by giving you an example of the kinds of things that we're talking about here. I'm going to be using the term transcription. Many people will have seen the term transliteration, and I'm going to avoid that for various reasons I'm not going to get into. But basically, this is the kind of phenomenon I'm going to be talking about. These are actually examples which are extracted from the web, doing something very similar to what Martin described. You can see basically the relationship. You'll see two a text in some script, and you'll see in parentheses something which is in a different script, and then you want to kind of vet that as being a reasonable transcription of the other term. And these are examples of various ways of writing these words in different scripts. Okay, so this is the kind of stuff we're interested in here. Okay, so there's some basic issues that we're going to be talking about, and I want to start by pointing out that we have a particular kind of application in mind. I give you, or you give me, a comparable corpus, so a corpus which is, say 2 news sources. They're about the same kind of topic, not necessarily translations of each other, in 2 different languages which use 2 different scripts, 2 different writing systems. And I want to go and find all of the names which are somehow related to each other. The George Bush or whatever in English and in Arabic and in Chinese and in whatever languages the corpora have.
So you want to form those lines?
I want to form lines like that, basically. That's the idea. So the kind of output that we saw on the previous slide. Exactly, right. So there are two kinds of issues here that come up, and that is there's the issue of co-occurrence of the terms. So if they're related, you expect them to occur in documents that are related. Now, in general, we don't necessarily know which documents are related, but at least in the worst case, you could say, okay, we know that these are two days of news in these two languages. Here's in English, a day's worth of English news, a day's worth of Chinese news, and they're about on the same day. So at least there's probably some related stuff in there somewhere. So that related documents could be as vague as that, okay? So that's one issue, and we expect things to co-occur in kind of reasonably similar time distributions. I'll give you an example of that on the next slide. The second issue is that we expect them to be phonetically similar at some level. Now, it could be based on the pronunciation, it could be based in part on the letters, but we expect some sort of similarity. Again, this is related to the issues that were just discussed in the previous section. Okay, so again, just to emphasize, and it's important to bear this in mind because this is going to be relevant for understanding why we pick particular evaluation kinds of measures that we do. And that is we're really interested in the problem of, given two streams of text, finding the related words. Okay? There's a different kind of application one could consider, which we're not considering here. That is, I give you a name in English, and you're supposed to tell me, without the existence of another corpus, what a plausible transcription into another language would be. Okay? That's also something that one could do, and people have worked on this, but I'm not going to be talking about that today. Okay? Just to give you an example of the time distribution, this is actually something from the Nunavut Hansards. These are, I guess, parliamentary proceedings in English and Inuktitut. And these are just two examples of place names, Nunavut itself, and this other name, which I can, Aglukak or something like that, in English, and its actual spelling in Inuktitut. And the point to bear in mind is these are documents which are related. In this particular case, these are actually translations. And the point is that the terms that are clearly related to one another have a very nice co-occurrence distribution. In fact, in the case of Aglukak, it's extremely good correlation.
How big is the Nunavut Hansard?
It's not huge. It's only a few 100,000 words. I don't remember the exact number. It's a few months worth of text. So it's not particularly big in this case. Okay. So I thought I'd just point out one thing here. So it's nice that the CLSP uses this kind of iconic symbol, the Rosetta Stone, which of course, as everyone knows, has kind of become an icon of language and language technology, language translation, all kinds of things. But it's kind of important to bear in mind that the importance of this particular artifact relates to exactly what we're going to be talking about today, namely transcription, because it was because of the fact that the Egyptians transcribed the names of the Greek kings of the last dynasties of Egypt, Ptolemy. It's because they actually transcribed it phonetically into Egyptian that people were, in particular, Jean-François Champollion and Thomas Young, were able to start to crack the Egyptian code. Okay, there's been a lot of previous work on this. One of the motivations for doing this in the workshop context, though, was because, as with many things, there's been a lot of work on kind of different corpora and different kinds of techniques have been proposed, and people have made progress on these issues. But one of the things we want to hope will come out of this is that we will have a sort of a common set of tools and a common set of techniques and sort of a better understanding of how to approach this problem so that people can actually sort of compare techniques. It's been kind of hard to sort of compare different techniques because people often evaluate and train and so forth on different corpora. Okay, so these are basically what we're going to be talking about. Actually, let me kind of skip to the next slide, which sort of says the same thing in a different way. Namely, we're going to be talking in the next few minutes about two issues. First of all, finding appropriate features for discriminative training, in particular string matching, so the sort of phonetic similarity or the string similarity between the two versions. That'll be Ting. Christy will be talking about score combination for combining both score and temporal information. And then I'll talk a little bit about the toolkit that we've been developing. As I said, one of the goals of this workshop is to provide a common set of tools, and one of the things we've been doing is developing a set of tools which we will be releasing that will allow you to do basically what I described at the beginning, and I'll say more about that later on. So with that, I'm going to turn it right over to you. So when I actually... Oh, I should say one more thing. Come on up. But while Ting's coming up, I just want to mention one other thing, and that is just something about the data in case people are wondering. We have a large number of lexicons. We also have this dictionary that we've been that I mentioned before, that we've extracted from the web, as with the dictionary that Sanjeev and Martin talked about, that have been extracted for the web for their sub-team. We will plan to give this away, and this gives dozens of pairs of languages. And then the corpora, for the most part, pretty standard corpora that we've been using. We're not going to be talking about all of these today, but these are the resources we've been using, so I'll shut up now and you can...
This interscriptal transcription is the same as transliteration?
Yes, as I mentioned before, I'm not going to use the term transliteration for various reasons.
Strictly speaking, transliteration means something else.
Oh, really?
Yeah. So, I mean, we can talk about that later. So it's not an interesting point. I just wanted to avoid that use of that term.
Oh, okay. Good morning. So our task here is to, given a pair of languages with distinct scripts, we want to find the best graphical and that is stream-based features for the purpose of finding the transcription pairs. So, well, we are mainly interested in 3 different language pairs. So the first one is English and Chinese, and the second one being English and Arabic, and English and Korean. So for all these dictionaries, we split them up in the way that we use 90% as a training data and 5% in header and 5% testing. And as we can see, these 3 language pairs are among the somewhat difficult language pairs because Chinese, Arabic, and Korean have very different scripts than English. English has alphabets, but usually they are not. They either English, Chinese, Arabic, Korean. Either they do not use alphabets, or they write that in a very different way than English. So we need to find some good features to represent those languages. And in the case of English, we use English letters, and we also have the festival derived from festival, the phonemes of English word, the pronunciation of those English words. And for Arabic, Chinese, and Korean, Chinese has an alternative orthography, which is a Chinese pinyin, and we used that. And for all the other 2 languages, and also with Chinese, we used the phonemic transcription, which is written as wordbat. And we use that as a string representation for these languages. So for those of you who are not familiar with the pinyin system, here's an example. It's sort of a quasi-phonemic transcription of the Chinese characters. Suppose we have 2 Chinese words here, and each pinyin string corresponds to the pronunciation of the characters. So as you can see here. And the reason why we prefer those strings, letter strings, is if you look at the example here, suppose this is a pair of transcription for the name, and this is an English spelling, this is a Chinese characters. And it's very difficult to align these 2 words here. The English word has 7 letters, and the Chinese characters only have 4 of them. And it's almost difficult to do that. But once we transcribe that into pinyin or wordbat, then it becomes a relatively easier job. So we experimented with different feature sets, and for the pair between English and Chinese, we used English letters to pinyin letters, and English letters to Chinese phonemic transcription, English phonemes to Chinese phonemic transcription, and the phonetic features derived from these. This is a relatively work being done. This work has been done before the workshop, so we used this as a comparison to our metrics. And for English to Arabic and English to Korean, we used the English letters to their respectively phonemic transcriptions. So once we know what what features we want to use, we actually produce them using this very simple sort of intuitive methods. We first get the bigram strings for each word, then this is a case of English word, and this is a pinyin stream of the transcribed English word. Then we simply do an alignment and couple the bigrams to form a pair, these pair features. And these features will be, because this is a correct transcription pair, and these features will be the positive features for our discriminative model. And we also, because a model will need negative features to let it know, okay, which cases are right, which are not. And we experiment with 3 methods to generate the negative features. The first one is the most intuitive one, so we mismatch the dictionary pairs. So for the, for example, the Clinton here would be matched with some words that are not Clinton. Or we can...
Go back, please.
Sure.
So the calendar there is the right way, so to speak, the right way of pronouncing Clinton.
Yes.
China.
Right.
So nobody in China would try to say Clinton. They would always say calendar.
Yes.
Even though they know English and know that it's no good.
Yes, right. That's the official pronunciation of that name in China.
Actually use it.
Yes. When I pronounce the name of the president, I will say Kelington instead of Clinton.
So your knowledge of English will not interfere?
Usually, no.
And in fact, it is actually appropriate that it's not, because he's trying to do interscriptal transcription. So he's trying to figure out how it will be written in Chinese, not how it will be spoken.
No, I know. I just asked the cultural question.
Okay, all right. That's a different question.
And also, all these pairs that you generate are not generated by EM or anything like that. You just take all combinations.
Right. It's a very simple algorithm, not an EM. Okay. So, yeah, we talk about this.
Wait.
Another.
Okay.
Within a Chinese character, is there a subset of, symbolic representation that will give you a few more letters, so to speak? Letters. Can you go within a character now and really analyze the character itself to find out? Because I realized that by watching a little bit of TV that most names are like 3, 4, 2 characters. So is within the character. Can you break the symbol now within the character?
The radicals.
It's. The answer is yes, but it would take us a long time to explain that.
Okay,
yeah,
fine.
So yes, but not in a way that's relevant for.
Right. Okay. So we also no more questions. Okay. So we also experimented with the second method, which is we shuffle the characters in one language. In the example here, we would shuffle the sequence of these letters, so make it a wrong example for the transcription. And this is the third method is quite different from the first two, and we come up with the idea, actually Chris suggested, we can use the nearest negative neighbors. So for the example here, Clinton, we would find the transcription with some word, say Clint or blind, something, blinden, like those, and we pair them up with the word Clinton as their negative neighbors, okay? And so we'll proceed to the evaluation phase, and we find that the best feature is actually the English letter to Chinese phonemic transcription. We were able to get an overall accuracy of 99.4%. This is very impressive. And the accuracy on the true positives are 97.7%. On the true negatives are 99.6%. So the reason why the model always scores better on the negatives than the positives is because we have a skewed distribution in the testing and also the training data set. In the testing data set, we have 4 times more negative testing cases than the positive cases. So if the model says, okay, I learned nothing, I say everything is negative, then it has 80% accuracy. But
what is the test here? So you're given an English word and you're given a putative Chinese pinyin.
Right.
And the model just has to say, is this correct pinyin for this word or is it not? Is that the test?
Yes, they're basically right, yes. And we have negative testing cases, say, an English word.
And the negative test cases are synthetic, like you just said. They're
yes,
not...
right.
Okay.
not all of them are synthetic. Some of them are real cases. Many of them are real words. They're just the wrong ones.
Well, yeah, the wrong ones. No, what I'm saying is that it's not like somebody accidentally used them somewhere and now you're deciding they're wrong. You created them.
We use the same shuffling mechanisms to generate the negative testing cases. Okay, so we want to make sure the effect of the training size is actually, so we can see some improvement when we use different training data. And the smallest training data, we only use the 500 examples, and the largest being 260,000. So we can see a nice curve here, and this shows some improvement if we increase the training size. But so the point here is more data is always good. It's always better than few data. But also, at a very early stage, we can get reasonably good performance in here, say 10,000 examples. The second best feature set is English phoneme to Chinese phonemes. And this is slightly worse than this, but the reason why this is worse because when the festival generates English pronunciations for the English words, there are possible errors in them, and that probably will cause difficulty cases, confuses the model a lot. We were actually surprised to see the performance of nearest negative neighbors are so bad. And the interesting thing here is actually the smallest data set have relatively the best performance on the positive cases. And as we increase the data set, it just purely drops to the stupidest model where it says, okay, I think everything is negative. The reason here, I think, is if you have a nearest neighbor, then actually a lot of pairs between the negative examples are positive features. So you got a real alignment between these. Only a very small part of them are different. And this confuses the model a lot. We extended the model to English and Arabic, then it looks reasonably good. But this is a very small training dictionary. And so there was something funny going on at the end of it. But it's still a reasonable performance. And this is a performance between English and Korean, which looks pretty good too.
Does this imply that English letters to Arabic phones does not work, or it's worse?
It's worse because the dictionary is much, much smaller. It only has 1,400 cases.
So let's see, around 1,000, I guess this is the F score is about 82. Go to the next one. At 1,000, yeah, over here in Korean it's 90.
Yeah. 90 to something.
And 1,000 examples.
Well, it is going to be worse for Arabic because of the vowel problem.
Yeah, but Arabic is an alphabetic language, so one could have used Arabic letters. Yeah.
Mm-hmm.
So,
no, we are, and the problem is that, as King says, the dictionary is small, but also there is this issue of the vowels being missing. That doesn't help.
Yeah, but I don't know about Korean. I don't think that's the same problem for Korean. So
no, Korean works better than
No. What I mean is you could have also explored letter to letter between the two languages.
Right. Actually, we do have data for that, right?
Yes, we do, but it's not so different from this one. Mm-hmm. Okay.
Excuse me, did you mention what training module you used?
The perception module.
The perception.
Mm-hmm.
Because for the negative cases, you said that things become very bad, but probably if you use some other training procedure, you wouldn't be so influenced by the
Right, we haven't done that yet, but the main reason here is, as I have said, the similarity between the negative cases and the positive cases confuse the model a lot.
That's why you need some other training procedure.
Right, okay. Okay, then I hand over to Christy.